Greetings, one and all. It is my great pleasure to welcome you to the 4th annual Martin Gardner Lecture. The previous 3 Martin Gardner Lectures were Jason Rosenhaus, Doran Schatzschneider, and Eric Demain. Martin Gardner was an amazing, creative polymath in many senses of this word, and so it's not entirely surprising that this year's speaker, in the last line of her biography, says, her guiding principle is that a professor's office can never have too many toys. She is an amazing player of mathematics and also of many other wonderful things, which she's also an incredibly good expositor. If you are a fan of the site Ravelry, which is a knitting site, and you look up her stuff, well, I haven't done it, but a professional knitter, who happens to be my daughter, told me, wow, she has good project notes. They're helpful, they're interesting to read, they're blog style. Most people don't have interesting project notes. Even the helpful ones don't. So you can see that she really cares about explaining things in ways that are not just clear, but also very entertaining. She's a professor of mathematics at St. Mary's College, and for about 3 years there was the Stephen Muller Distinguished Professor of the Sciences. And in the larger mathematical community, she's highly active. She's a member of the Bridges Organization Board of Directors. That's a huge math and art organization, a co-organizer of the Bridges Math and Fashion Show. She's an associate editor of the Journal of Mathematics and the Arts and one of the 24 mathematicians and artists on the Math Alchemy team. Her amazingly wonderful book, which she just signed for me, and I'm so glad, on crafting conundrums, puzzles, and patterns for the bead crochet artist, was with the computer scientist, Ellie Baker. And just in case you want to know, I mean, we're talking about being wonderful and award-winning. A set of bead crochet jewelry pieces that's related to this topic won the prize for the best textile, sculpture, or other medium in the art show in 2015 joint math meetings. So it's my incredibly great pleasure to introduce to you Susan Goldstine, who will be speaking on Maps of Strange Worlds, Adventures in Topological Art.
Thanks. Hello. I realized too, I think this is the last of the invited lectures, so if we could maybe just take a moment to thank the MAA for organizing a fantastic conference. So taking some advice from earlier today, I'm going to start with a story. And the story begins in 1852 when a math student, a student of Augustus de Morgan named Francis Guthrie, sort of brought up this question involving maps. He'd been coloring a map of the counties of England and started to think about how many colors he needed to color it to achieve the goal of coloring in regions and maps, which is to make them easier to read. And so to make a map easier to read, you want to color the regions so that neighboring regions are different colors. And so the question that Guthrie posed was, how many colors do you need to color in an arbitrary map? So let's say crayons are really expensive. How many do you have to invest in if you want to be sure that you can color any map in the world? So his conjecture, based on his experience with this map, was 4, and he brought this up to Augustus de Morgan, for whom this was new. Part of the reason that we know that this happened in 1852 is de Morgan that day wrote a letter to William Rowan Hamilton saying, hey, my student has this interesting question. Now, I will note that there are definitely specific maps that require fewer colors, but what is definitely true, and what was apparent to them at the time, was you definitely need at least 4 colors if you want to be able to handle any map. Now, as mentioned before, I teach at St. Mary's College of Maryland. It's a beautiful public liberal arts college in southern Maryland. So the first place I went was a map of the counties of Maryland, and it turns out they're just not geometrically interesting enough. But I grew up one state north in Pennsylvania. So here is a picture of the map of the counties in Pennsylvania. And I'll call your attention to a couple things. One of them is, this is as it appeared on geology.com, which is where I pulled this from, and it is already four-colored. So it is an illustration of the fact that, at least for this map, only 4 colors are required. But I want to call your attention to a particular region there. This is where it gets interesting, because I'm not sure that I actually remember the names, and these are all rather far away from me, but I believe that's Lycoming, Northumberland, Montour, and now I'm blanking on what the fourth one is. Columbia, thank you. Those 4 counties, if you look at their borders, they all touch each other, right? So right there, that's an instant, sort of real-world demonstration that we need 4 colors for some maps. This map, those 4 counties have to be 4 different colors. So the question was, is that always going to be enough? So this question was first published a short while later, in 1854, somewhat confusingly by F.G. And part of what makes that confusing is that Francis had a brother, also a math student, named Frederick. So it's not entirely clear whether this is Francis Guthrie or Frederick Guthrie or some other mysterious F.G. But by 1860, Augustus de Morgan had published the problem, and de Morgan was considerably more famous. So the problem got on the radar, and people started to be interested in this and to try and prove the conjecture that 4 colors are enough. And luckily, they did not have to wait for very long, because it was only a short while later, as math goes, in 1879, that Alfred Kemp proved the Four-Color Theorem. So, great. Except no. And this is a famous enough story that I sort of figured that the people who know the story would have an inkling of this. People believed that the Four-Color Theorem had been proved for quite a while. It took 11 years, but 11 years later, Percy Haywood came along and published a paper where he said, I'm really sorry, the proof doesn't actually work. And by the way, there's another lovely little detail here that I somehow had missed in my reading of the history until fairly recently, but actually that wasn't the end of everything, because there was another proof of the Four-Color Theorem by Tate. In 1880, which I've left off just because there's already, quite a bit of information here. And 11 years after that, that was found to have a gap in it. So, shucks. But Percy Haywood did not just destroy, he did actually achieve some things. He was not able to rescue the proof, but what he was able to do was to prove the 5-color theorem. So 5 colors are definitely enough. And that's kind of the maddening knife edge that mathematics sat on for many, many years after that, right? We knew that 5 colors were enough. We knew that you needed at least 4, but which was it? And then there was an astonishing breakthrough that was actually reported, as many things in mathematics that are sort of colorful and interesting have been over the years, by Martin Gardner in his Scientific American column. It was actually kind of an amazing blockbuster breakthrough. He had a column in which he said, oh, hey, it turns out you actually do need 5 colors. Here's an example. This is a map that requires 5 colors to color in. So people tried to color in this map. It's actually quite hard to color in. Gardner got a bunch of mail that sort of went, no, I've colored this in. I only needed 4 colors. What are you talking about? The problem was that people had not sort of noticed the fact that this was his April column. And in fact, this was part of his now infamous April Fool's column, in which he announced 6 amazing breakthroughs that had absolutely not happened. And this was one of them. And he was just in time, because this was just about the last point that he could get away with this, because the next year, in 1976, Apple and Haken announced that they had a computer-assisted proof, which was sort of an interesting thing to ponder. So what had happened in the meantime is the mathematician Hayes had started to think about how you could actually prove the Four-Color Theorem. And in the 60s and 70s, he'd worked on this method that basically said, suppose you have a map that needs 5 colors, and then you play around a little bit and you figure out that there has to be some particularly thorny configuration somewhere in the middle of it. And if you can find all of these configurations and show that all of them only require 4 colors, then you're done. And now you're in the realm where a computer theoretically could help. And so Appel and Haken were the ones who actually carried this out. And it was announced, and this was controversial and confusing. Because first of all, the proof was not in any reasonable sense human readable. The proof involved the computer checking 1,800 and change cases. And in fact, they were all verified by people. It turns out that Appel and Haken sort of like pressed their families into service and went, hey, check these for us. But you can't really with a straight face say that, and then they understood the proof, right? And so this ignited some really interesting discussions about, well, but like, wait, what is a proof actually? Why do we write proofs? Does this count? I think the view on that has changed over the years. I think what everyone did agree is it was certainly not a satisfying proof. It was actually kind of annoying, because a good proof like teaches you something about why this is, and this was just... and to make matters worse, in the early 80s, mumbling started to go around that the proof had problems. There was a master's thesis that found an error and whatnot, and so behind the scenes, Appel and Haken sort of, scrambled and got things together, and they did eventually both acknowledge that there had been errors in the proof and corrected it. So a complete and correct proof was published in 1989, 13 years later. So like somewhere between 11 and 13 seems to be the time period for these things. And at this point, it's pretty well accepted that the four-color theorem is proven. But unless there have been any news breaks that I've missed, there's still not a human-readable proof. There's been some improvement, so just to give you sort of an illustration of the kind of improvement that there's been, and this is not the most recent development, there are one or two after this, but Robertson, Sanders, Seymour, and Thomas, first of all, came up with a faster algorithm for the computer to actually four-color a map. So it was, did it more efficiently than what Appel and Haken had. And they managed to get down to a smaller number of cases, so it went down from over 1,000 to under 700 and over 600, so it's still a lot. So it should go without saying that I cannot prove the four-color theorem for you today. Nor would I want to, right? I mean, but I would really like, to the extent that I can, to give you an idea of the flavor of what a proof like that looks like. Because if you think about what's being asked by this proof, it's a pretty tall order, right? You have to take every map that's ever existed, every map that could hypothetically exist, and somehow prove an abstract fact about all of them. And maps can get pretty complicated. So if we want to have a sort of better understanding of how all of this works, we're going to need to talk a little bit about the structure of maps. And in particular, the kind of maps that we're talking about here obviously tend to look a little bit more organic when they're happening out in the world, but they are maps that are like geopolitical maps. So you're basically taking, let's say, the plane, if it's a map on a piece of paper, and you're dividing it up into a bunch of regions. And there are going to be points in this discussion where it's going to be kind of useful to consider maps on spheres. I'm going to make a claim here, and I invite you to think about this. You can ask me about it afterwards. But basically, it turns out that coloring a map on the plane and coloring a map on the sphere, they end up basically being translatable one into the other, sort of the way that we have flat maps of our roughly spherical Earth. And so this is a map, let's say, on a plane or a sphere. The regions are also sometimes called faces. For notational reasons, I will be using faces for the most part in this talk. And the fact that we might be considering these maps as being on a globe is also going to motivate our counting the region outside of the map as one of our faces. So for example, the map that I have drawn here, we have the 5 faces as marked. Right, so this is our first piece of data on this map. I want to add a couple more pieces of data that allow us to look a little bit more closely at how the countries are interconnected, or the regions, right? These could be countries, it doesn't really matter, the different faces. And so we can break this down a little bit further and see that we have these boundaries between the countries, and we can highlight a couple of other features. There are these, and this is one of these weird plurals, so I have a vertex pointed out there, and then vertices is the plural. Those are the places where multiple countries come together. And so in particular, you'll note, as you're looking at this, that at any vertex, at least 3 countries have to come together. Because if you only have 2 countries, then you haven't hit a vertex yet. You're in the middle of an edge, right? And so there's also an edge marked here. An edge is going to be a segment of border that separates 2 and only 2 countries, and it will connect 2 vertices, right? So in particular, even if some of these curves actually were drawn as single lines, each edge is just going to be from one vertex to the next vertex. And so with these definitions, we can go ahead and count up the numbers of those as well. And what we find is that there are 9 edges, and there are 6 vertices. So I'm going to take that data and I'm going to do something. And one of 2 things I believe will be true. Either you are expecting me to do this, or you will be very confused, right? So this is one of those, sometimes we have this moment, just bear with me. There is a reason for this, because there are patterns that some mathematicians have noticed. And one of them is, if you take an alternating sum of these numbers, so if you take the number of vertices minus the number of edges plus the number of faces, the patterns can be interesting. So for this particular map, with the numbers that we have there, v minus e plus f turns out to be 2, right? And so here's the cool part. It turns out that if you look at other maps of this type, then you do the vertices minus edges plus faces count, you always end up getting 2, with some provisos. You do need your map to be one connected cluster of countries, so you can't have like a thing here and then another thing over here with no edges and countries connecting them. And there are a couple of other technical points that I'm not going to say now, but think about those if you like. That's another sort of like, what are the ways that you can break this if you draw weird countries or weird edges of various types? Here I've just sort of diagrammed this for kind of sub-maps of the map I started with. I would also invite you to go and draw your own examples. Do the counts, and as long as you have a single club of countries, you remember to count the outside region, and you count everything up right, you should find that you get 2. And you can sort of think about what would go into proving that that's true. A very nice approach, it kind of echoes what I did here to make these pictures. If you have a complicated map, you can think about what little pieces of the map could you pull away, and how would that change the vertex, edge, and face counts. And if you convince yourself that they never change as long as you don't, disconnect things or make a map that's unacceptable, then you have an argument. So this formula is commonly known as Euler's formula, which is not to be confused with Euler's formula or Euler's formula. He did a lot of stuff. At any rate, very, very useful, and it's a very strong abstract fact that applies to all of these maps. So I want to see what this looks like in connection to a sort of idealized version of that 4 counties in Pennsylvania submap that we looked at. Namely, we'd established that we need 4 colors, and here is sort of the simplest, most abstract version of a map where we have 4 faces, right? And the green, orange, and purple ones are triangles. And I'm going to argue that kind of the yellow is as well. I mean, it's a face that's bounded by 3 edges. Okay, if you don't buy that, then this is actually one of the places where it can be helpful to think of this as a map on a sphere. And if you happen to, crochet, which I think may have come up in earlier discussions here, I have to figure out where this particular thing went. See, I originally had these stacked nicely, and I think I may have confused myself. One of the things that's actually pretty easy to crochet are polygons of various types. Oh, here we are. So you can go ahead and you can crochet basically granny squares, except forget a corner. So these are 4 triangles, and they fit together into this map that I've sort of push the triangles in a bit so you can see the shapes a little bit better, but like if you kind of puff this out properly, you can see this is a map on a sphere. And it's basically the same map that we see there, right? And I want to look at the v minus e plus f for this, but I want to look at it abstractly, as if we could not hold this in our hands, right? So I have it here, but you know, forget that for a moment, might pull it out again. Just from the information about what the countries are and which ones touch, can we work out vertices, edges, and faces? Well, the faces part is pretty easy, right? There are 4, because that's kind of how we set all this up, right? So we have 4 countries. If we do it in this configuration, they're all triangles. So we're taking 4 triangles, we're attaching them. The number of edges, well, we have 4 triangles, so there are 3 sides to each triangle, which means we have a total of 12 sides to work with, right? But each edge in the map is going to be part of 2 triangles. So 12 should be twice as big as the number of edges. So in fact, the number of edges will be the 12 sides of all the triangles divided by 2 to account for the fact that we're fastening them. And in fact, in the picture or on the crochet model, you can see, yep, absolutely, there are 6 edges. For vertices, we do have to look a little bit more at the actual configuration in the map, but you will notice, and I think it's particularly clear on this model, that there are 3 triangles that come together at each vertex. That's part of the reason why when you puff it out, it sort of looks fairly round and uniform. And so the number of vertices is going to be, again, the total number of corners of the triangles that we have to work with is 12. 3 for each of the 4 triangles, but now they're being attached together in groups of 3. So the number of vertices is going to be 12 divided by 3, which is 4. And then if you do the Euler Formula calculation, you see, yup, great, we got 2. Okay, so let's now look at the question of, could we have 5 countries, each of which touches all the others? And of course, we have some meta information here, which is that the answer has got to be no, because if you could do that, then that's clearly a map that would need 5 colors, and someone would have noticed that in the last century or so. But I want to get at, like, how do we actually know? So do we need 5 colors? And just to be clear, this is way short of a proof. Even if we can show that you can't have 5 countries that touch each other, there are still countless maps that we have to check, like you have to do the April Fool's map and, you know, all sorts of other maps. But this is sort of like a little bit of a glimpse into the sort of tools that we have. So if we're setting this up abstractly, we have 5 countries. They have to touch all of the others, so each one has to touch 4 countries, which means they should have 4 sides. So they will be quadrilaterals of some stripe. I will go ahead and represent them as squares. So we have 5 faces. Those faces are squares. And for convenience, I'm going to name them A, B, C, D, and G, because E and F, not good names. So we have 5 faces. And now we can do some other counting. And I actually want to jump over to the vertices, even though that's the harder one. I'm going to jump over to the vertices because, well, it depends on how many squares come together, right? You could have 3 to a corner, you could have 4 to a corner, you could even stick all 5 of them around one corner, and then trying to figure out how to glue it is a little bit rough. But we do know that at each vertex, you have to fasten together at least 3 squares. Right? Because if you only have 2 squares, then again, you're not at a vertex yet, you're at the middle of an edge. So we have a total of 20 square corners to work with. And each time we form a vertex, we have to take at least 3 of them out of this pool. And so we could pull out sets of 3 corners until we get up to 18 for a total of 6 vertices, and then we are stuck. We don't have enough corners left to make another vertex. So I don't know exactly what the number of vertices is, but I do know that it is no bigger than 6. Right? Because we just don't have enough corners to make more than 6. And now, if I look at what we're trying to find here, we have V minus E plus F. V plus F is no bigger than 11. So in order to subtract the number of edges and get 2, it has to be the case that the number of edges is no bigger than 9. And here's why that's a problem. So now we can actually start being a little bit more specific, like what edges do we have? Well, A has to border B, C, D, and G, so that's 4 edges right there. And then that takes care of A, but B also needs to border C, D, and G, so that's 3 edges. And C still has to border D and G, and that's 2 more edges. And perhaps you've detected why I stopped. Because the problem is, we're already up to 9, and we're not allowed to have more than 9 edges, so that means D cannot border G. So we've just shown that this scenario is in fact impossible. Okay. Again, not a proof of the Four-Color Theorem. There are tons of other maps. In fact, I want to show you another one. This is one I've actually also built out of Crochet, and that's the reason why we have this nice little document camera here. Not actually supposed to be displaying my phone per se. So I have a crocheted object here that it's sort of bent up in a somewhat confusing way, which is why I think I need to manipulate it a little bit and sort of move it around. But first of all, you'll notice that if I flatten out one of these regions, what I have here is a hexagon. And I'm not going to have time to flatten all of them out, but just take my word for it. These are hexagons. Maybe we'll flatten another one out. But before I get to that, so they're hexagons. How many of them are there? Well, the nice thing about flattening out the white, I just want to make sure that I actually have this in position here, is you can kind of see little bits of the other hexagons, and so there appear to be 6 hexagons around this, and in fact, they are colored red, orange, yellow, green, blue, purple in rainbow order, almost as if I made it that way on purpose or something. So there are at least 7 hexagons. In fact, there are only 7 hexagons. If you sort of, fiddle around with this, you'll see that no colors other than those 7 come up. And if you take another hexagonal face and flatten it out, the colors won't be in rainbow order anymore. But you can see the same sort of thing is happening here around this green face. The green hexagon is connected to every other hexagon. So what we have here is 7 faces, each of which touches all the others, which was supposed to be impossible. Now, in fairness, I didn't actually prove that. I proved that you can't have 5 regions, each of which touched all the others. And this should feel harder than that. But granted, you can also account for that, because let's say I take this same crochet, but instead of crocheting these 2 hexagons in green and yellow, I instead crocheted them white. That I'd have one big white blob and 4 other colors, and everything would touch everything else. And so the answer to what's going on with that is that up until now, I have been, I wouldn't say lying, I've been suppressing. I've been leaving out a very important detail, except implicitly. And that detail is, I had mentioned that we were looking at maps on the plane or the sphere, which I claim basically amount to the same thing. And this proof only works if we are on the plane or a sphere. And for what I'm discussing next, a sphere is sort of the easier one to put in there. This is not a sphere. And the way that I know is because I can do this to it. I can't do that to this. I could try, because the crochet is a little bit porous, but there's no channel passing through this. This surface is a sphere. This surface, well, if you could sort of puff it up and untwist it, it's kind of a donut surface. Or, if you want to be all mathematical about it, this is the type of surface that we would call a torus. And it turns out that on a torus, the rules are entirely different. In particular, it requires 7 colors to be able to color every possible map on the torus. Fascinatingly enough, this was actually known long before the Four-Color Theorem, both that you need 7 colors and that 7 colors are enough. In fact, that paper that Percy Haywood wrote back in 1890, he actually proved the result for the torus. and some more that we'll get to later. So now, this is the point at which, and I know we're not really set up for this, but I feel like people should sort of like get to know their neighbors and people at other tables as they're moving around. So I'll let this circulate as far as it can get if you want to take a look at that. And I will go back to pictures on the slides. So let me come back to that v minus e plus f. So I'd said v minus e plus f is always equal to 2 with my fingers metaphorically crossed. That works if you're on the sphere, and so you can think of that as being an inherent property of the sphere. If you make a map on the sphere and you make sure that you don't have any sort of like weird disconnected things, then v minus e plus f will be equal to 2. That number is called the Euler characteristic of the sphere, and it's represented by the Greek letter chi for characteristic. But if you were on another surface, like a torus, then you're going to end up with a different number when you take v minus e plus f. If you do it carefully, because if you just sort of like, say, draw a little polygon as one country and count all the vertices on a torus, and that's it, you're going to get 2 again, because you're going to have this one big country that's like this messed up punctured torus. And that doesn't count. So to actually get the Euler characteristic, the rule is your map has to be made so that each face could be laid flat, right? You might have to stretch it and bend it a little bit, right? So you have to cut it up into that many pieces. And one way to do this is there's this sort of nice way to cut apart a torus. In fact, for those of you who've had topology, you may have sort of seen this diagram running in reverse, where you glue together the sides of a square to make a torus. The map that I'm looking at here is the one that's at the beginning of this line of arrows. And so you'll see we have a blue circle that goes around sort of like the equator of the torus, and a red circle that goes around the short way. And the rest of the diagram is mostly just cutting apart across those lines so that I can make the case to you that this map does properly leave us with one country that we can lay flat, right? So you cut along the red line, that gives you something that you can straighten out into a cylinder. You slit, and that's the red circle. At that point, your blue circle has been cut apart into a line segment. You cut along that, you lay it flat, you get this square. That is a legit flat country, right? So if we do the count here, how many vertices are there? Well, there's just the one. It's just the place where the 2 circles intersect at the back of the torus, right? In the square, those 4 points all get glued together into one vertex. So there's one vertex. The edges, well, they're color-coded, right? There's a blue edge and a red edge, so that works. So there are 2 of those, and there's just the one face. And so what we find here is v minus e plus f ends up being 0. So 0 is the Euler characteristic of the torus. And if you like to play around with these sort of things, you might want to sort of generalize and say, well, what about if I have like a torus, but instead of like stamping out one passage that goes through the blob of whatever material I have, I stamp 2 so that there are 2 holes or 2 handles on a blob, 3 handles, 4 handles. Well, in general, you can put in as many holes as you like into your torus. The number of holes is called the genus, and the general formula turns out to be for a G-hole torus, v minus e plus f always ends up being 2 minus twice the genus. So it continues the pattern that we've seen here. When you take a sphere and sort of do whatever surgery you need to do to have a hole passing through it, you lose 2 in your Euler characteristic, and that keeps going. So let's take another look at abstractly the crochet map that's going around now. So what we have here is, instead of 4 triangles, we have 7 hexagons, right? So that's 7 regions. The edge count, again, pretty straightforward. Each side of a hexagon, or each edge in the map, is going to be 2 sides of a hexagon. So the total number of sides that we start with is 7 times 6. We divide by 2. There are 21 edges. That's way easier than counting them on that one. And the vertices, well, nicely enough, there are always 3 hexagons to each vertex. This is sort of a nice regular map, kind of like our little spherical one as well. And so to get the number of vertices, we take the the 42 total corners that we have of all the hexagons, divide by 3, and we find there are 14 vertices, and sure enough, when we take v minus e plus f, we get 0, which is good, because that's what it's supposed to be. It's a torus. Yay. I do want to make it clear, I am not the first person to think of crocheting hexagons and sewing them together and making this. The earliest example of this that I know of was made by Moira Chas, who does all sorts of really amazing things with crochet and topology. You should definitely check her out. On Instagram, she is Crochet Topology, so relatively easy to find. And so she made this map, but it's a bit hard to see what's going on. I only put one of the 4 pictures that she has of this in the place where she published it. And even with those, it's kind of hard to see how the countries fit together. You may also be experiencing that in passing the map around that we have here. So she has actually crocheted some others that are a little bit easier to see. So here are 2 variations on that map where the 7 countries have been, sort of stretched in an appropriate way that make it a little bit easier to see what's going on. And so there are some quite lovely renditions of this. There are many more that she has, but that's just sort of a little bit of a representative sampling of her single torus work, and we'll get to a little bit more a little later on. But I should also make it clear, this is not where I entered this story. I didn't see Moira's work until after I already had become mildly obsessed with map coloring. So the starting point for me was the following. While I was still a postdoc, met a couple of mathematicians, David Lahavi and Tamar Ziegler, and they showed me this mug that they'd made. David had come up with the design, and Tamar had actually made it out of like real pottery with a kiln and everything, which is amazing to me that people can do that. And they sort of handed it to me and said, hey, do you know what this is? And it was a 7-color map, and that was really cool. I wanted one really badly. I don't do pottery, but I knew of the existence of paint your own pottery places. So, this is technically not the first one that I made, despite the caption. This was about try 3. It was the first one where I felt like I'd actually figured out how to do the glazing properly. And so this was basically me having studied the mug, remembering sort of the tricky thing that they did with the colors around the handle, and then literally like taking markers on a coffee cup and like marking them until I was pretty sure I knew what I was doing. And at this point, I was hooked, because these maps are fun to make. I also like this one because it does tie very well to that old saw about a topologist not being able to tell the difference between a donut and a coffee cup, like the fact that this is using that single handle as, hey, Taurus, super fun. So I started to sort of like fiddle around with this more and collect more of these. In fact, again, I've got at least one more of them here. Actually, let me not put that there for later. Yeah, here we are. So here's one. I think I can just toss this like so, that you can take a look at. It's basically the hexagon one, but sort of stretched out so that it's a little bit easier to see what's going on. And I'd started to post them online, and that meant that I started to like find out about other ones. Interestingly, one of the ones that I found out is this painted hydrostone Taurus that was in Norton Starr's office. And this is a little surprising to me because he was one of my math professors, and I was in his office numerous times, and I'm still not entirely sure whether I just totally didn't notice that it was there. He did have a lot of stuff, very good on the lots of toys. Or if it's that he didn't make it until afterwards. But this is a particular 7-color map called the Unger Map. And one of the things that's nice about it is you can actually see all of the color connections from one view, which is super cool. The back of this is actually kind of boring looking. It sort of looks like a candy cane. The countries wrap around the way they would need you to connect. But you can see the connections really well because it's all symmetric. And then, for example, if you look at the white strip that wraps from the inside to the outside, on either side of it, white touches red and purple, and then at the coming up from the inside it touches yellow and orange, coming up from the outside it touches green and blue, so you get all of the colors and everything's symmetric, so yay. And I also found out about this set that was made by Sarah Marie Bell Castro and Carolyn Yakel. By the time I knew about this set, I had fallen into the orbit of the knitting circle at the joint math meetings, and they are the ones who founded it, and I would attribute a lot of the explosion in mathematical fiber arts to them. They've been hugely influential that way, and they made these appropriately enough for the 7th, get it, gathering for Gardner. They actually made the postcard that that image is taken from and gave it as a conference gift. So as I said, I had these online, and that did turn out to be a little more significant than I was expecting, because I think it was November of 2008, I got an email from someone I'd never heard of named Ellie Baker. There's been a little bit of a spoiler in the introduction, so hopefully you have a sense of where this is going. And this email from Ellie Baker said, hey, my daughter and I have been working on making bead crochet bracelets, and the designs are really hard to make. We're very confused, but we're figuring stuff out, and we wanted to look for mathematically interesting designs, and we saw that Unger Taurus on your website, and we haven't figured out how to do it in bead crochet yet. But my daughter, who is currently a senior in high school, so this is her daughter, Sophie Summer, came up with her own pattern for a 7-color Taurus. Here's a picture. Hope you like it. And I wrote back and went, oh my God, that's great. Can I please add it to the page? And there started a furious email correspondence and collaboration. So in particular, in 2009, we put together, and then it was first exhibited in 2010, and when I say we, it was really Ellie who sort of combined the work from all of us. These are bracelets that were designed and made in some combination by Sophie Summer, Ellie Baker, and myself. And this was actually the first piece that I ever had in one of the mathematical art exhibits. This was just Ellie going, hey, do you want to put something in? Sophie went off to college and has gone on to bigger and better things, but Ellie kept asking these really cool questions about bracelets, and so eventually that turned into the book that you saw before, which I had not brought with me, but now I can go, hey, see, look. Big as life. We are actually currently working on the 2nd edition, so knock on wood, that should hopefully be coming out next year. And that's really been sort of the richest collaboration of my mathematical career. So, if you would like to make your own, another piece of this collaboration is in Math Horizons, put out by, you know, some professional organization or other. There is actually a paper that we wrote in 2013, the three of us, about making exactly these maps that show a 7-colored torus. And there's a pattern in there for 3 different sizes of them. We also made a YouTube tutorial video to go into it, which is not a bad way to sort of pick up bead crochet. And so I have, and I feel like maybe these should sort of be scattered in different directions at this point. I'm sort of tempted to just like wing them to random people in the audience, but that seems like that has to be some sort of safety violation. So what I have here is the smallest size as shown in the article. This is the largest size, and this is that same largest size you can actually make in big glass beads, and if you have a small enough wrist, it will fit. And so if you are feeling adventurous or you happen to already bead crochet, you can actually make these yourself in a way that's a little bit more accessible than some of these other venues. So we, you know, weren't the only ones who sort of got obsessed with this, so there are more. In fact, the page that I have now, I have updated it somewhat, but I did realize as I was thinking about this that the ones by Eve Torrance in the bottom row, I still haven't posted, so I will have to fix that. So the 2 on the bottom are different styles of modular origami. Skana Britton's is actually a belt that she made, and she explained to me that she sort of figured out her own map, and she doesn't really like the warm colors, so she deliberately set it up so that she could wear it and only have the colors that she likes on the outside, which I thought was quite nice. Ellie Baker and Kevin Lee collaborated on this really cool scarf that is basically one of these. it happens that I saw her last week, and she had an extra one of these. So she said, yeah, sure, you can borrow it and hand it around to people. And I feel like this is floppy enough that maybe I can, if you're comfortable, pass it to you. But this is one of the renditions of that pattern. And so it's sort of like 7-color map meets Escher, which I thought was kind of nice. So we sort of have like the fashion world and the origami world there. Now, you're not going to just stop there if there's somewhere you can go from there, right? You can look at how many colors do you need on a 2-hole torus? How many colors do you need on a 3-hole torus? And in fact, and also surprisingly, in 1890, in that original paper, Haywood actually wrote about that as well. In fact, there's a formula. And you've probably figured it out already from the pattern that you've seen so far. The formula is obviously this, which is just the most bonkers formula. It's really nuts. In particular, the outer symbol is the floor symbol, meaning you have to round it down for the most of the time that it's not even an integer, right? So yeah, super wild. So Haywood actually proved that this number of colors is sufficient for everything except the plane/sphere in 1890, which just, it's amazing. It's not just that the four-color theorem is crazy hard to prove, it's the only case. I don't understand why. So basically, the overarching story here is Haywood actually proved that you can do it with this many colors in 1890. And he started working at the other end. So as I mentioned, he drew a 7-color map. And other people had sort of filled things in, but it took a while for people to fill in all of the different genes that you can have. And so eventually Ringel and Young sort of filled in the last gaps, and it was completely proven that this is the number. You need this many, and this many is enough. And if you take the Haywood formula, you find that if you have a 2-hole torus, aka a double torus, you need 8 colors. And of course I had to try and do this. But at the time that I was thinking about this, in light of painting mugs and things like that, the only examples that I had, to be honest, weren't even all of these. I had seen the examples on the left, and I know that the one at the bottom does not appear to be a double torus, but it's part of this really cool trick where you can knit hyperbolic baby pants. Ask me about it later if you want. It's in one of their books. You can get to it at one of the references I'll get you at the end. And if you fold up the legs into the waist in the right way, you get this double torus, right? And so I knew that this had been done, but like, I can't figure that out. Like the Carolyn's one that's unfolded, I don't know where the colors are, I can't say. I just couldn't wrap my head around that. I am not sure if I had seen the picture from the Tietze textbook on famous mathematical problems yet, but even if I had, too complicated. So when I wanted to try to adapt this, what I did was I kind of went back to first principles, the way that we did when we were looking at the hexagons. And I said, okay, if I want an 8-color map in the simplest way possible, I am looking at 8 countries which touch 7 others, so I want 8 heptagons. And I know the number of edges, because that's easy. You just take like all of the total edges, divide by 2, like we did before, and so you find there are 28 edges. And then it gets trickier, because who knows what's going on with the vertices. But this is the point at which I go, oh, right, this was a double torus. I can use that fact. So I'm putting this on a 2-hole torus. I know that the genus of that, and that is, that is great. The genus of that is 2, and so if I look at the Euler Characteristic formula, that tells me that v minus e plus f should be -2. So if I take the data that I have and solve for vertices, I find that there have to be 18 vertices. And then the cool part about that is you can work out that if every vertex had 3 octagons around it, you'd be just a little bit short. That would sort of burn up 54 of the 56 corners that you have to work with. And so the most symmetric solution that offered itself was you make these 2 clusters of 4 heptagons each, and so that sort of burns up those 2 extra corners, and then everything else is 3 to a corner. And basically, I sketched this out, and then there were like 10 pages of notebook scribblings from 2009 or 2010 or something, and eventually I found a way that they fastened together. And you are so not going to be able to follow this now, but you can look up the paper if you like. If you sort of rearrange this picture, you find that you can interpret this as the two halves fold together into two punctured tori. So a torus, but you've cut a little bit of the surface out, and then you can glue them together. And down at the bottom is what the colors look like where you glue them together. All 8 of the colors touch each other in that part. So as long as you do that part that way, everything else will come together as long as you get each color in a single region. And so my 2 applications of this were the stacked T set has 2 handles. The boundary between the 2 tori, like the puncture, is where the cup touches the teapot. And so I had the arrangement there. This one is a little pendant that I have here. I'm not going to pass this around because this is a little delicate, but if I could have you switch to the document camera here. So this is 8 color 8, which has never actually been worn as a pendant, but that I've used for exhibit things. And I thought it was quite entertaining during the introduction when the the jewelry set came up because, yeah, that's what I'm wearing, if you were wondering why. So what I ended up making for another art exhibit is, this is a 2-hole torus, but I made it longer so I could sort of attach the back. And so the 8 colors all touch each other around this thicker central band, and then you sort of have the two holes out on either side. Oh, and see, this is perfect because I was just starting to lose the position on here. So the trick, the necklace, and hopefully I won't make too much noise when I remove it, is I had to lift it up so that it wouldn't get in the way of the microphone. This is a pendant that has a 7-color torus on it. And thank you. And I made it a little bit more decorative, so I sort of fancied it up, but it also kind of has this nice feature. It's a little bit harder to see than the Unger map, but you can see most of the connections there. The sad part is you never see the back, and the back actually also kind of looks sort of cool in its own right. And then the earrings here are, because you have to have the whole set, right? So those are 2 little planar maps, and since they're 8 colors, I was able to put 4 colors on each. So this is map coloring jewelry set, and all told, it has the double torus, the torus, and the genus 0 cases. So that's one of the more fun pieces that I've ever made. Now, I am either very short on time or out of time, but if I can, well, actually, leave the document camera on for just one more second, because I want to take a moment to show this. And I would pass it around, but there's little enough time that maybe I'll leave this up front. What I actually ended up doing in 2020, it didn't occur to me until then that I could also just literally take those 8 heptagons and crochet them and sew them together. And it works, which was kind of a surprise to me. So this is the sort of test version of this piece that I made that is here if you would like to take a look at it. It's a little smaller than the real one, so easier to pack. But if we can go back to the slides. And before I do that, I also want to point out other people have actually used that framework. So there is Moira Chass's rendition of the sort of 7 heptagons warped framework that I wrote about and made those 2 pieces from. And Eve Torrance, at the same time that she started playing around with taking Sonobe modules and making 7-color maps, also did this 8-color map. This piece is the Granny's Double Torus piece that I have up here, and right there, that is my topologist colleague, appropriately enough, Sandy Ganzel, demonstrating that it does actually have 2 holes in it. They're sort of at right angles to each other, which was kind of a delightful surprise. And this is still ongoing, because just last week, we had the Bridges Conference in Halifax, and all of this stuff was happening there. And what we have there includes some 3-hole tori in various media, some more symmetric maps. The one down in the lower right is particularly interesting because it's based on a sculpture called the Roupidon, it's a made-up word in French, that is sort of the mascot of the Maison Poincaré, which is a new math museum that the Henri Poincaré Institute is opening. And Sylvie Benzoni-Gavage was actually doing a workshop where she was talking about coloring those in. The outer shape is the intersection of 2 cylinders, you know, the classic calculus thing. So, cool. So, that's kind of what I love about this, is not only does it have this sort of story that stretches back and all these different people got involved in it, but to this day, even though letters and questions in classrooms have been supplanted by phone calls and emails and Zoom meetings and so forth, there's still this large group of people who are excitedly talking about this. And Mara Chas was not at Bridges, but she is continuing to make higher genus models and have her students make them and find their own maps. So I hope that you will also be motivated to look at this more yourself. And there is the slide that you want to take a picture of if you want some of the sources. Also, as someone who helps run the Bridges Conference, I would be remiss if I didn't point out that the entire archive of over 20 years of conference papers is available online at any time. The Google search is a little wonky, so I would recommend going to the extra features and searching for author names. So thank you very much.
I think we don't have time for questions, but I'm sure that Susan would be glad if you came up and asked her for stuff. And if you have some of her beautiful artwork, if you could bring it back to her, I think she would like that too.
Please
Thanks.
do. And if you want to look at some of the things that were too delicate to pass out, they're here.
Let's thank her one more time.